Okay, let's begin. So just a quick reminder, right, of what we covered last time, only because, right, these materials and these concepts are, subtle or, yeah, right. I mean, or you won't remember them all when you first see them, but they're essential, right, to absorb, okay, for us to move forward, even for the next few lectures. So I guess start all the way down here, sort of the message is somewhere here. That basically, let's see here. Yep, this slide right here, right? For a state, right, there are three key quantities that we use to classify it. And there's no telling, right, which quantity will be best suited in which scenario, okay? Most likely for now, we focus on these two guys, right? But this will show up in like two lectures or so. But basically, right, the point is you should know what they mean. The symbols we use won't change. We might kind of enlarge the symbol to like talking about moving from state I to state J. But now, right, it's just basically the visits or returns from state I to state I. But, right, you need to know what they mean because we will use the same symbols, right? How they should be for recurrent and transient states and their connections. Again, right, not easy. And the whole point of this lecture is to point out those connections, right? So, for example, right, this guy, Fi, right, for transient state, Fi is less than 1, right? And for recurrent, Fi is equal to 1. All right. Vi, right, will be finite almost surely, or probability Vi is finite is 1 for transient. And probability Vi is infinite is equal to 1 for recurrent. Okay. Now, of course, right, this translates to expectation of Vi is infinite as well, right? But expectation of Vi for transient, expectation I, right? I guess here there's all I here. I means we start at I, right? Expectation of Vi is 1 over 1 minus Fi, right? For transient. I guess this equation makes sense, right? For transient because Fi is less than 1. But you can also kind of, with some sort of abuse of notation, right, say that it also works for recurrent because, right, 1 over 0 can be thought of as infinity. So this equation actually is beautiful in the sense that it sort of generalizes, right? But so that's the connection, right, between Fi, Vi, and what they mean, right, for the states, right? But they also, so this also has another link to the transition matrix, which is the sum, right? P to the NII, sum from 0 to infinity, right? So this, right, links the transition matrix to the expected number of visits starting at I to, right, the return probability starting at I, okay? So that's everything in a nutshell, okay? But like, of course, in between, there's like kind of the definition, the connection, the communication, division to classes and everything like that. And also, right, there is this use, right, to prove that for finite state Markov chain, we must have at least one recurrent state or, kind of generalize that, right, to a recurring class, right? And the proof, this is a rewrite from last time, goes through the number of visits, right? And the idea is pretty simple. Because you have finitely many states, each state is visited finitely many times, so the total number of times you spend in all those states must be finite. But don't forget that we're in the infinite time horizon context, right? So that would somehow involve some kind of contradiction. Okay. So again, I mean, you can kind of go through the details and work through them, but the point here is to be able to be familiar, right, with these concepts and be able to use them very efficiently. Key in point, for example, right? When we want to prove, for example, recurrence or transience, right, are class properties, then sort of, right, really, right, this is one of those typical questions that you will see in the problem set as well. Prove something, right, along the line that I recurrent, I communicates with J implies J recurrent, right? So you need to be able to, right, state the criterion, right, for recurrent. And here, right, that we list the possible approaches, right, basically through the three quantities. And that's the strategy of proof that you have to go through anyway, right? But some of these may not be easy. And some of them might be easier. All right. And that's the point. For example, right here, we point out that if you try to go through FJ route, all you have, right, from the communication hypothesis is that, you know, because you communicate, right, from J to I and from I back to J, the probability of ever return to J is positive, okay? But that's not what we want, right? For recurrent, we need it to be exactly one. So it's not that, notice, right? Of course, here we only use the communication hypothesis and we haven't used, right, the recurrent hypothesis of I. So, of course, we're not saying that that route is impossible, but at least it seems not easy to somehow, right, throw in the recurrent of hypothesis into, right, this kind of like so-called path analysis, because, right, you try to analyze, right, the possibility of ever returning to J, right? And also be aware, right, that the word path analysis now is a bit more subtle because the path here, right, has infinite horizon, right, is the word ever. So when you say ever return to J, you have to be very careful when you insert, let's say, a point in between, because you might insert it in a non-meaningful way, okay, without realizing it. For example, right, ever returning to J or ever returning to I, whatever, right? So you know Fi equals to 1. So you know that I will return to I with probability 1. But the catch is this is at a random time. All right, you do not know the exact time it will return. And in fact, right, there's no such exact time, right? It will return at a random time. What random time? The random time Ti, right here. So, right, this is just to point out that, right, there are a lot going on here that is not the same, right? It's your typical like Markov chain path analysis to begin with. And not that that was easy, right? Anyway, so here, right, the approach using this is not impossible, but might be difficult. So the approach via the number of visits actually is more promising because we do have the identity of the sum. And we just have to show its equivalent. Okay. So again, we showed this last time, right? We talked about this. It's not new, but now we're kind of like reharping, right, on the technicalities. And there are a lot of technicalities, right, for this. And in fact, this will be a theme going forward. The subtlety, right, of how to string these concepts together and string them together correctly and understand the concepts correctly, because you know, kind of blink and you miss it because like you might confuse, right, one concept with another. And that's actually very, very easy to happen, right, in a place like this. Okay. Any question about this? All right. So now back to the problem set. So we were looking at, no, not this. This problem, right? And this is actually a very, very cool problem, right? Because what does it say? It says that basically a recurrent class, right? If it's recurrent, I'm just saying it's recurrent, cannot have any arrow going out of it. Arrow as in, arrow of accessibility type, right? The reason, right? I guess the intuitive reason is kind of easy to see, right? A recurrent class should be like a closed balloon, whatever, right, by itself. If the balloon is not leaking, well, all well and good, right? The amount of helium in there is preserved. You travel around. But if as long as there's a leak, right, no matter how small or how much remote, like a small probability, right, eventually it will leak and eventually you will go out, right? So you cannot stay in the class forever. And so that's why. Or, right, put it another way, in the language of the F notation, if I is recurrent and J is transient, what this says is Fij must be equal to 0. Okay. Again, right, this is not just symbolic playing around. If you think that I'm just writing down something that blah, 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 well, you're missing the point and probably you're not even trying to follow the lecture. But if, right, you try to follow, then see that this actually has some meaning and it's actually a rather, right, I mean, it's not a deep statement or anything like that, but it does try to capture some property, right, of the Markov chain. That is, you can never, right, go from a recurrent state to a transient state, right? There's no accessibility, right? Okay, any question? Right, so now so how do we prove this, right? And we were here last time, right? And let's kind of talk about the logic here a little bit. I have too many, so let me pull up a new one. Right. So the logic right here, just to kind of help us, right, go through the problem. Because basically, intuitively, somehow we want to go through the contradiction route, right? Meaning that, because the only thing we can pin on, right, is this quantity being 0. So, we try to see what if it's positive and blah, 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 right? If Pij is positive, we want to show a contradiction, right? But contradiction to what? And so also, so notice, right, we mentioned last time that the status of J in this problem, right, is not given. J can be either transient or recurrent. That's not given, right? So you cannot assume anything about J. So why did I put the Fij equal to 0 just recently, right? For I recurrent and J transient. The reason is I was just kind of talking about a special case of this, right? Because of course, if one is recurrent and one is transient, then I and J cannot communicate to begin with, correct? So I was kind of doing a specific example, right, of the implication of this problem. I'm not saying that this problem really implies that J is transient. Does it make sense? Right, but so the logical problem does not, right, say, so there are two possibilities, you will. J transient or J recurrent, but belonging to a different recurrent class, right? But so you could try to separate the cases, but probably, right, it's not necessary that way. But anyway, right, so we don't know anything about J, okay? And so if Pij is positive, we want to imply a contradiction. The contradiction must be to the hypothesis. But I want to point out that, right, the contradiction should not contradict the I recurrent. The I recurrent is a standing assumption that's not negatable, or that's not the target of negation. Do we understand? Because actually, again, I know that it's just the way the problem is written. If you read this problem, you feel like, well, I can negate I being recurrent, no? But when you kind of look at the spirit of the problem, right? Pij positive, and you can never really negate I being recurrent in any way, because you don't have enough information to conclude that if you let go of the hypothesis I recurrent, and you have nothing to work on, right? So again, think about it very well. But the statement should be really like this: I recurrent, untouchable. Okay. Then, right, if I does not communicate with J, it must imply that I doesn't go to J to begin with, or Pij is go to zero, right? In one step. That's all it is. So, right, I recurrent, untouchable. Then, if you have Ij does not communicate, implies Pij equal to zero. That's it. So the target of negation is I not communicate with J. So the target negation here is to prove that Ij communicates somehow. Do you understand? So that's the logic, right? So do not try to negate I being recurrent. That's not the target of negation here. Okay. So having said that, right? Any suggestion for how we should approach this problem?
Yeah, my idea here was that if Pij is greater than zero and I is recurrent, then for some number of steps k, there must be some pathway that you can go back from J to state I.
Good, good. And actually, right, that's sort of like the middle step here. Somehow you must be able to show that P to a K J I is positive for some K. And that's, right, sort of seems like, right, the intermediate step you need, right, to prove Ij communicates, but you only have I goes to J. Okay, but then how do we show that? How do we show we can go from J to I in
My
some step? Yeah, go ahead.
my assumption there was just that it's given that I is recurrent, and we're just making that as a standing assumption.
Correct.
Pij is greater than zero. So
Yeah.
for I to be recurrent, there has to be a pathway back.
No.
So
No.
is there a step I'm missing?
Well, no. Yeah. So to be clear, right? You're not missing anything, but notice it the peculiarity of proof, right? And we are talking about proof here, is to be very weary of saying something that sounds very obvious to you, but not obvious to everyone else in some way. Because what your statement is saying is, right, okay, I know I is recurrent, so Fi goes to 1, right? And Pij is positive, that's the assumption. Then it must follow that P to J I K must be positive for some K. Meaning, right, if you kind of take a step back and see what you wrote, you're kind of saying, wow, the conclusion must follow without further explanation. Do you understand what I'm trying to say?
Yeah,
I'm not saying that you're wrong,
I-
because that is a conclusion, but the proof is you have to elucidate this, right? You have to insert more. Why? For example, why would that be? Or we need to throw in something that is super clear, right? That logically forced. Okay, let's follow Rever's statement spirit a little bit, right? Because I guess what you're saying, right, is what if this doesn't hold? Then what happens? What does that mean? Let's pursue that thought a little bit. If this doesn't hold, then what happens?
In that case, then I would go to J and then not return to I,
Good.
making
Then
it
in terms of the quantities that we're listing, what would that make? What would that affect? What quantity would that affect?
Fi would be less than 1.
Excellent. Fi is less than 1. Correct. So if Fi is less than 1, what are we saying in terms of statement, probabilistically?
That the probability of returning to state I is not 100%.
Or there is a possibility of not returning to I ever, correct? There's a possibility of never returning to I, correct? So having said that, it probably makes sense for us to look at 1 minus Fi. Right? And analyze this. Okay? Because we know that it's a zero quantity, right? What can we do about this? Well, we can look at, we can lower bound it by some quantity. You know, the trick is very simple. This is 0, right? You lower bound it by some quantity. If this quantity is positive as well, then the squeeze will force this quantity to be 0. And we can do something about it. But we will lower bound it, right, by a logic, right? Which is exactly the path we're looking at here, right? You do not return to I, right? You never return to I. That's through a lot of steps, right? Correct? But one possibility is to go from I to J. And then from there, what do? Never returning to I. So I use FJI here in that sense. FJI is the possibility of ever returning to I starting from J. Does that make sense? So, right, this statement is very simple. What it says is, to never return to I, there are many possibilities, but one possibility is to go from I to J and then never return to I starting at J. That's 1 minus Fij, FJI. Do you understand? Now, right, because Fi is equal to 1 and Pij is positive, this would imply Fji is equal to 1, right? Because this has to be 0 and this is positive, so this is 0. But Fji is, let's write out Fji, is probability starting at J that you are at I for some n, right? Or if you want, the probability is you are at I for some n, given that you start at J, right? So if you will be at I starting at J for some n, what does that mean? I mean, this is guaranteed, right? Is equal to 1. This means P to the n Ji must be positive or something. Does that make sense? So, yeah, go ahead.
No, I just thought I was just saying that made sense.
Yeah, so I'm not saying that this is anything super crazy above and beyond what Riva was saying. It actually just elucidates using symbolic arguments, okay, of what I guess Riva had intuitively, right? That basically, if you don't have a path to come back, then there's a chance you will never, you're not guaranteed to return back to I. Once you recognize that, then the quantity you want to analyze is this quantity. And then you can bound it by logic because this implies that. And then it follows, right? Again, a bit subtle, all right? But you could write this proof in a lot of blah, blah, blah way, like verbal. Again, I'm not saying that that is necessarily wrong, but within the verbal argument, you could go circular, meaning you start to assume what you will need to prove, or you just kind of go directly to the conclusion without saying things, right? And that's the challenge. Any question here? All right. So the next thing is, right, just for fun, or not for fun, to calculate Fi, right? And just to demonstrate that, right, Fi is not easy. We never say it's easy. But when we look at this transition matrix, we establish, right, an equation, but that equation may not be easy to use. So it's just really exploring, right, the possibility of calculating Fi. So in this matrix, right, what do you think F0 is?
Is it 1/6?
That's a very fascinating argument. So you say F0 is 1/6. Okay. Do you want to explain? Can you explain?
Yeah, I got that from P01 times P10, because if it goes to state 2, it's absorbing.
Okay, so great, right? So actually what Riva was doing is exactly what we call first step analysis, right? So F0, right, is equal to, right, probability, let's say you go to X1, right? So something like this, right? Sum, right? F I0 P, okay, let's say P0I Fi0, I runs from 0 to 2. Do we understand? Right? So, okay, sorry. Let's do this. Actually, is still incorrect. If you go from 0 to 0, you're done. Because, right, you have to return to 0. Otherwise, you can go from 0 to I, then return I to 0. The reason why we have to separate this, right, is because f of 0, right, may not be 1, okay? F0 is a return probability, right? So, but here, when you go from 0 to 0, you're done, right? So this is, you understand? So that's the first step analysis. Anyway, here, IP000, so we don't have to worry about that. But that's the first step analysis here. Any question about this? Okay, so now let's plug in, right? So we can go from 0 to 1 or 0 to 2. So that's 1/2, right? Times F10 plus F20, right? Okay. Now, if you're at 1, right, what happens? If you're at 1, then you can go back to 0 with power 1/3. But if you go to 2, then you're stuck. So claim F10 is 1/3. Correct? That's clear. Because again, 2 is absorbing. And very similarly, F of 20 is 0. Both of these because 2 is absorbing. So reverse analysis is correct. But, right, I'm not sure if Riva would write all these things down, but this is what you should write down notationally. And the logic being used is first step analysis. All right, any question here? All right. What about this? What's the answer? If you're thinking about this, you're thinking too much. The answer here is why, right? Because this is a irreducible Markov chain. All states are recurrent from what we talked about before.
To prove this, would we have to use like anything further than that?
No, you can quote what we proved. I mean, the whole point of the lecture is not only to introduce you to concepts, but also give you some results you can use, right? Some results that are, let's say, a bit painful to prove, right? So let's not reprove them, right? So yeah, finite irreducible Markov chains are all recurrent, right? That's clear. You can use it.
Okay, thank you.
Well, but we understand, right? Actually, there's actually a small logic step here, right? What did we prove though? We prove a finite Markov chain must have at least one recurrent state, right? That's what we said. But then, right, because it's irreducible, well, everything's connected to everything else, so everything is connected to that recurrent state, so everything must be recurrent, right? So there's actually a small logic there. It's not just obvious. We didn't write down this statement exactly. We had two small statements that would make this up. All right, any question? I think that's it, right? Yeah, well, the solution would calculate all this, but ignore it. It just calculate for fun, right? This is enough. All right, any question before we continue? All right. So the next lecture will focus on a important topic, right? Rather a subtopic of Markov chain random walk, specifically one-dimensional random walk, right? And there are two topics. I mean, there are a lot you can say about the random walk, right? 1D random walk. But one obvious topic is about the behavior, right? Like recurrence transient of the random walk. But this is, of course, the infinite random walk, right? And then the gambler's ruin problem is exactly the same setup, but it's rather finite in this way. That basically you have two bound, right? 0 and n. And you start at a state I, and you move left and move right, right? With probably P and Q. And you ask what's the probability you get absorbed, right? At one end rather than the other, right? Because getting absorbed in one end, right, is not ruin, and the other one is ruin, right? Like a gambler, right? Betting bet, right? And he will win a bet with probably P, right? Losing a bet with probably 1 minus P. He can either win his fortune or go broke, right? So it's a finite random walk, but in the context of what we're looking at, this one-dimensional random walk actually has the taste of calculating the probability of eventually going to state n from state I, right? Because state I here, any state here is transient in between, right? And there's two states, 0 and n are absorbing or recurrent, right? And so we are calculating the probability of going from I to the absorbing state n rather than to the absorbing state 0. Do you understand? Sorry, give me a moment. I'll be right back. Okay. So now, to motivate, right, the random walk, let's ask a very simple question. And the question, right, is okay, the first thing to note about the random walk, right, whether, finite or infinite, right, whatever, is a 1D random walk is irreducible, meaning I communicate with J for all Ij. I mean, of course, right, for the gambler's ruin, well, okay, let's just look at the infinite random walk first, okay? But the gambler's ruin is almost true, except for the absorbing state, right? So is this clear that for a random walk, all states communicate with all other states, right? That you can always go from one state to another. Is that clear? Do we need to prove this, or because it at least like P, right? You can have something like if I is less than J, right? Then I can go to J with probability P to the J minus I, right? And J can go to I with probability 1 minus P, right? To the J minus I, right? At least that much. Are you okay? Meaning you just walk left or walk right, right? And you will get to the point you want. Now, the question, right, is not about that. But remember, we just talked about it. When you have an irreducible finite Markov chain, or let's just look at a finite Markov chain. Forget about the word irreducible for now. In a finite Markov chain, right, we said that at least one state is transient, correct? We say at least one state is transient. Sorry, I'm not even paying attention. At least one state is recurrent, right? Meaning not all states can be transient. All right. So the question is, imagine, if you will, is there a Markov chain where all states are transient? Is that possible? That's a question. Is it possible for there to be a Markov chain where all states are transient?
No.
The answer is yes. Yes.
I thought we had to have at least one state that had to be recurrent. Or
Of
did
course,
I?
of course. No, you didn't miss. But what you did not look at carefully is the if and then. If what? There is a hypothesis there. If the chain is finite. So, right, there's room to play around there. In other words, right, again, this is not a guarantee, but one implication is that the chain must be infinite, right? And that's actually very simple to think of. Transient means you never return, right, to the state. So you start at some state, you will eventually never return to it. That's transient with probability 1, right? You would eventually escape. Sorry, with a positive probability, rather. Sorry, right? It's not probability 1. You have a positive probability of never returning, right? So, or you will spend only finitely many times at that state, rather, right? Then you will have to go somewhere else, and then you have to go somewhere else, right? But the point is, right, eventually you run out of room to go if the chain is finite. But if the chain is infinite, no problem, right? It's very easy to think about. Well, you can, for one thing, right, keep going to the right, right? I mean, again, right, that's a very small probability, but, right, at least it's imaginable. If you just follow that path, in fact, you will only visit each state once, right? And then all states are left of 0, you never visit, right? So it's possible, correct? So in fact, right, the 1D random walk is very important from the point of view of counterexample, in the sense that it demonstrates an example where all states can be transient. And second of all, which will concern us later, when it's symmetric, then it's recurrent. And this actually already kind of, you have to think about, and that's not, this actually is already subtle, right? Symmetric means you go left and go right with probably 1/2 each. But we claim it's recurrent. What does that mean? We claim it's recurrent. That means if you start at 0, you're guaranteed to return back to 0. But does that even seem obvious here? My claim is no, right? Not really. Again, right? Because of the possibility that the walk will keep drifting to the right, and not coming back. Does that make sense? So of course, one thing that's very much lacking in all these things that we say, and this is why, right? I say you have to be very careful when you get to this stuff, is the quantities must be put down. The calculations must be done, right? We cannot just wave our hand and say, yeah, it seems like it will return, or it seems like it will escape, blah, blah, blah. So yes, right? No, we have to prove it. But so I would say that both of these are subtle, right? And a lot of the lecture will be devoted to just exactly showing you how you can approach this proof rigorously. But that's not the end of the story yet. The end of the story actually will lead to the next lecture, the word null here, is that we will use it to distinguish with the phenomenon of positive recurrence. What that means is, even though, right, you're guaranteed to return, right, to this, the expectation of the return time actually is infinite. That's why it's kind of weird. Meaning that, right, yes, you're guaranteed to return, but you will have to wait forever on average for it to return. Okay, so that's no recurrence. And so that's why the 1D random walk or random walk on the integers is important from all these points of view. It's when you ask a question, can a Markov chain do this or do that in terms of classification of state, a random walk can come up as an example to take care of this. All right, any question? Okay. So, right, so we talked about this, right? So go to right, go to left. So that's right, that's just really writing it down. So again, right, going back to the fundamental, right? To classify a state in any chain, right? We look at 3 quantities: Fi, Vi, or expectation of Vi rather, right? And Ti, right? The first return time. This will be not prominent for now, right? It'll be prominent in the next lecture. But so we'll look at these, right, and apply them to the random walk and show, right, that they have the desired properties for recurrence and transience. Namely what? For the return probability, right, we will show that the return probability is 1 when p equals to 1/2, and less than 1 when p is not 1/2. And the same thing here, right? We'll show that p equals 1/2, this happens. And remember, right, the key here is through the sum. So basically we'll work with the sum, right, to show that this sum is infinite when p equals 1/2, and this sum is finite when p is not 1/2. Are we okay? So those are the 2 approaches. Let's say 0, 0, right? Any question about this? All right. So first of all, right, the random walk is irreducible. So we can only, right, and in fact, right, there is even more than that. All states are actually exactly the same in terms of random walk, meaning that, right, they in some way, right? So they there's a symmetry in the random walk. We'll look at that later. But basically, right, all states communicate. So all states share the same status, right? That either they're all recurrent or they're all transient. So we only have to look at one state, right, to establish that the whole chain is recurrent or transient. And so let's just look at state 0 and look at this sum. All right. So that's actually, right, approach number 2, right? We look at this approach first. Okay. So let's see here. I think we're at the quiz time, so let's stop here, and then we're gonna return to this after the break. All right, any question? So for the quiz, well, all right, let's have you do this one, right? Okay. So let us continue after the break. Okay, let us continue. You guys can still see the screen, right? Is the screen okay? Sometimes the screen doesn't come through.
Yeah, we can see it.
Okay, cool, thanks. So, right, so to recap, right? This is where we were, and we want to, right, compute this, right, or show is finite or infinite for the random walk, right? So of course, for the random walk, or actually, right, note that basically p to the n I whatever, right, usually is very complicated, right? Why? Very simple. You have to raise a matrix to n power. That's hard. But notice the random walk actually, right, it has a very simple structure, right? A state only goes to any two adjacent states. So from that point of view, we can write down actually p to n 0, but easy for the 1D random walk. Okay, so let's see. Can anyone tell me what they think p to n 0 is? Okay, so remember, right? Step right is p, step left is 1 minus p of q, right? Express this term in terms of n, p, and q. Not easy, huh? Okay, let's start small. What's the smallest n we can start? The smallest we can start at n is 2, right? So notice there's also that aspect. To start at 0 and return to 0, you need an even number of steps. Obvious, right? Because exactly how many steps you go right must be exactly how many steps you go left. Correct? So what's p2? 0, 0. P squared 0, 0. Should be 2p 1 minus p, right? Do you agree? Well, p4. What do you think? How do we go from 0 to 0 in 4 steps?
We would have to go 2 left or right, and then same the other way.
Okay, so is it p squared 1 minus p squared?
Is there a coefficient in front of that?
Yeah, what is that?
Is it 4? Or is it 2?
No, more than 4 actually. You think about it. It will be.
Oh, I see. Give me a second.
Mhm.
When- Is it 8?
No, less than 8. If you're counting manually, it's a bit cumbersome. I think it's 6, isn't it? And I know it's 6 is not just because not because I count manually. Shouldn't that be just 4 choose 2?
Yeah, of course.
Right? Out of 4 steps, you choose 2 steps, you walk right, and the other steps you walk left. Namely, right, left, right, right, left, left, things like that, right? So do we have a clue now in general? What's P to 2n 0, 0? That would be 2n, choose n, p to the n, 1 minus p to the n. Are we okay? And our task, right, is to prove the sum n from 1 to infinity, 2n choose n, p to the n, 1 minus p to the n is either finite or infinite, right? Depending on p equals to 1/2 or not. Notice that if p is equal to 1/2, this actually simplified to no. One half to the 2n, right? Like that. So for example, right, we declare that this sum is infinite. Right? So that's the goal. And so notice, right, again, I'm not trying to advertise that this is any easy or obvious or anything like that. But the point is the tools we have developed, namely, right, the sum is finite infinite, leads us to something that, you know, you can ask ChatGPT these days, or right back in the old day, you can look up in, let's say, an analysis textbook or something like that, right? Or think about it for yourself, right? But so it leads to something tangible that we can analyze. All right, but let's focus on either one of these, right? Maybe this is a bit more, let's say, concrete. What that means, right? Because if you want, right, this is 2n factorial and then factorial squared, right? How can we show that this sum is infinite, for example? All right, so this actually leads back to your calculus 2 education, right? Where you look at the conversions of infinite series. And well, right, I mean, in a structure like this, you could try to use like root tests, ratio tests, and things like that, right? Let me see here. It actually never occurred to me to use root tests or ratio tests, like ratio tests. I wonder if ratio test is inconclusive here, because the conventional approach, right? So my guess is, right, when it comes, so the conventional approach when it comes to this, when it comes to this step, then the next thing they would do is to use Stirling's formula, okay, to approximate the factorial terms. And then from there, right, deduce the conversions or diversions of the series. But so from that point of view, if they have to use that tool, I guess the root test, the ratio test is inconclusive. But right, this is, I just want to point out, this goes back to your calculus 2, right? Education-ish, where you try to analyze the conversions or diversions of a series. And so, right. So this is what I was saying, right? So Stirling's formula for n factorial is like so, right? And so if you, and again, why? The y is to just basically approximate, right, this when n goes to infinity. Because basically the behavior of this term, right, you're summing over it. So the behavior of this as n goes to infinity will dictate, right, the conversions or diversions of that series, right? And so if you plug in n factorial, right, into the 2n, right, you have to do some work. It will basically simplify down to this. And so, right, the sum will be like this, or the terms will be like this, or the sum will be 4p 1 minus p to the n over root pi. All right, so this is where I can stop because this actually does reduce to, right, your Calc 2 education. Can we prove now that if p is equal to 1/2, this diverges? And when p is not 1/2, this converge? Anyone remember their Calc 2 education and how to do that?
Is it L'Hopital's?
No, that's very far from it. L'Hopital is to take limit of a ratio when both top and bottom goes to 0, goes to infinity. This is not L'Hopital. Let's see, right? If p equals to 1/2, right, then this reduces to, right, forget the root pi, right? 1 root n. Correct? What is this series called? This is called the p series, with p is equal to 1/2, because it's n to 1/2. And you can do integral tests here if you want, but the point is, or comparison test. If p is between 0 and 1, the series will diverge. So when p equals to 1/2, this reduces to a p series. Now, well, p not 1/2. When p not 1/2, then the only thing you can conclude is p 1 minus p actually it's less than 1/4. The reason is p to 1/2 is actually the maximizer of that product, right? It is the maximizer of that product. That product is maximized at 1/4 when p equals 1/2. So when p is not 1/2, right? Like you can check, for example, p is like 1.1/3 or something like that, right? You can check that that's that product, right? 1/3 times 2/3 is 2/9, right? It's less than 1/4, right? So therefore, this entire series looks like a to the n over root n, where a is between 0 and 1. Right? A is actually 4p1 minus p. So this is like a geometric series being tempered by a root. The geometric, right, or actually this is an exponential decay. The exponential decay is much faster than the root blow up. So overall, or actually, no. Actually here, in this sense, actually the root n actually doesn't hurt, it helps. So in fact, you can just directly compare it to the a to the n, because the root n helps. It just makes it smaller, not bigger, sorry. If you have a root n up here, it hurts, but even that won't affect the convergence. But here it helps. So it's less than this, but this is convergence because it's geometric. All right. So that's it. Okay. So that's kind of a step down the memory lane for some of you, I hope, to Calc 2. Not that we need this in this class, right? But it's kind of go to showing, right? Math is really a comprehensive subject, right? You cannot say, well, I only choose to know this and I don't want to know that. You never know, right? What subject area you need for a particular problem. But like for this one, right, the tool we use is series analysis, because, right, the criterion we come up with is an infinite series. And so, right, Stirling approximation and some series analysis shows us the conclusion. All right, any question about this? All right, so I think that was what I just said, right? Now, my guess, right, is that that argument probably doesn't impress too many of you, even the more dedicated one, right? Because it's called the analytical proof, right? It you know, for the people who pay attention to analysis, that's the only ones that probably like that kind of proof. But nevertheless, I emphasize the legit nature of it, meaning that, you know, sometimes that's the only way you go through. That's why if you want to be a math major, you have to take at least an analysis class or something, right? But okay, still, right, this is a probability class, so maybe, right, that's not quite, let's say, in the spirit of the class, whatever that means. So let's try another, let's say, more to the point, right, to the spirit approach, which is the probabilistic approach. So let's try to calculate, right? So here we give it a different name, but it's really f of 0, right? Okay. And this is the so-called first step analysis, right? So just like how we just solved that homework problem, you can write this as this. That's actually that notation. Are you okay? Now, of course, right, unlike the homework problem, this is not direct, right? What is this? Right, with the homework problem, right, if you carry it one more time, then because 2 is absorbing, right, that's done. But in terms of the random walk here, right, here's 0, here's 1, here's -1, right? What you're saying is if I go from 0 to 1, right, with probability P, then I will look at the return back to 0 from 1. Okay, fine, right? But if you are at 1, you can either go to 2 or you return to 0, right? So, and same with -1, right? So the story doesn't stop there, right? It is not that simple. And this is why, right? This is a sophisticated object. But at least, right, let's continue, right? So again, right, then I call it F10, right? So, or you know what, whatever, right? Let's call it alpha, but that's F10, right? So let's say the crazy thing, if you will, is you continue the first step analysis one more time, right? This is actually pretty interesting in math that, right, while it seems like it keeps on going forever, you just take one more step to see what the heck is going on anyway, right? Because, right, you have nothing concrete to say here, So let's just continue one more, right, with this. So of course, right, one more time, then you either, right, so f10 is either, right, so you either go back to 0, and then you're at 0, right? You're done. Or, you know, God forbid, you you know, move one more step to the right, and now return, right? And now you have to return 2 steps. So this is f20. Are we okay? And the key, right? The key observation right here is f20 is f10 squared. And that's the key observation to help us stop this analysis. Because, right, if you have nothing going on here, then you have to move on to the 3040, and the game never stops, right? But the key here is, right, so you analyze from 0 to 1, right, from 1 to 2. But you analyze, then you recognize that 2 going back to 0 is actually the square of going to that from 1 to 0. And so, right, it basically gives you a closed system, closed equation for alpha to solve. Right? But can anyone explain to me why f20 is f10 squared? At least do you understand the spirit of the argument? What should f20 be equal? At least, like, let's say, conventionally. That's what it's supposed to be equal. Right? Now that is obvious, and you can just use that. Why so? Because, right, to go back from 2 to 0, to ever, right, go from 0 to 2, you must go from 2 to 1, and then go from 1 to 0. Are you okay with that? And now why? Then of course, right, the argument will close when you say f21 is equal to f10. Right? But why is that true? Because of the kind of the symmetry, right, of the random walk. Meaning that, right, 2 to 1 behaves exactly like 1, 2, 0. We're not saying 2 looks like 0 or 2 looks like 1 and 1 looks like 0, right? But 2 to 1 looks exactly like 1 to 0. Any question about this? And so, right, what we end up having is a quadratic equation for F10. Right, that we can solve for in terms of P. In case you get lost, right, in all these details, what are we trying to do here? Someone remind me. What is it that we're trying to do? Or, right, we already kind of not even sure what we're doing, just writing down some symbols. What we are trying to do is to prove F0 is equal to 1 or F0 is less than 1 in the two cases, right? In the case when P equals 1/2 or P is not equal to 1/2, right? And we can do that by somehow studying the F10. Because notice, right, when P equals 1/2, then we can solve for F10 right away and plug that in. And F minus 10 by symmetry will be equal to F10, right? And when P not equal to 1/2, then we can look at, again, but we can look at them and kind of do some more sophisticated analysis. Let's do the same. Right? Any question here? And so, right, if you solve this quadratic abstractly for P, right, for alpha, then you got these two roots. Now, if P equals 1/2, then you see that this is equal to 2. Sorry, P equals 1/2, this is actually a double root, right? This is also 1. So alpha equals to 1 is the only root. But already, right, that actually is a good sign. Because what does it say? If P equals 1/2, then this is 1, meaning, right, which makes sense. You're guaranteed to return to 0 from 1. And you're guaranteed to return to 0 from -1. So, of course, you're guaranteed to return to 0 from 0. Is this okay? Okay. If P is not equal to 1/2, then the two, right, cases are not symmetric, meaning that F10 is not equal to F minus 10. And so here, right, the claim is that in this case, F minus 10 must be 1. In other words, right, here, right, the random walk has bias to the right, right? So this is P, right? This is 1 minus P. It's clear, right, that if it's biased to the right, then somehow you can prove that F minus 10 is 1. So here, right, actually, let's take a look at this, right, here, to show you. This actually just try to make you think, but you can turn the situation around, right, and analyze this when P is less than 1/2. Okay. If P is less than 1/2, right, notice this is the root, right, of this equation, right, for whatever value of P it is, right? So if P is less than 1/2, what is this root? Then 1 minus P, right, is bigger than 1/2, correct? then if you take something bigger than 1/2 divided by something that's less than 1/2, what is the net result? The net result is something bigger than 1, correct? So in the case when p is less than 1/2, meaning you have a bias to walk to the left, then the two roots, right, the two candidates for F10 are either 1 or something bigger than 1. Of course, right? In that case, you conclude F10 is 1. Do you understand? So you flip the argument, it's exactly the same as this one. Nothing more. Right? Any question here? And then, right, you look at probability, right? You ever return to 0, right? As right here, right? So in this case, right, you know, F minus 1, right, is equal to 1. And F10, right, will be less than 1 from the same argument. So that's that, right? So if you sum, right, these two together, right, you will get 1 minus p plus alpha p, right, which is 1 plus p times 1 minus alpha. Let me see if that works. Sorry, 1 plus alpha minus 1, right? And because alpha less than 1, alpha minus 1 is less than 0, this whole thing is less than 1. And so f of 0 here is less than 1. And so in that case, right, this is transient. Any question here? All right, so this is to show you, right, that even though, right, we claim that we're doing probabilities and, you know, first step analysis, things like that here, right? These are not that any easier than, let's say this, right? It's just a different taste, I think, right? It depends on whether you feel like you want to use the analytical tool to, you know, analyze the infinite sum, or you want to use like first step conditioning and somehow, right, really be clever and, right, use the symmetry to work on solving for the probability, right? And that's a challenge or a problem. I mean, it's hard to say at the beginning, okay, this approach works, this approach doesn't work, who knows? Sometimes people try both, right? And depending on, you know, how they see things, maybe one approach will seem easier to some people than the other, right? But, right, the recap here is for random walk, right, infinite random walk, p equals 1/2 is recurrent, p not equals to 1/2 is transient. Okay. All right, all good? Any question? All right, so now let's go to, right, the last topic for today's lecture, the gambler's ruin problem. And so we described the gambler's ruin problem, right, already. It's like the random walk, right? But you start at I, you have n here and 0, right? I between 0 and n. And you go to the right with probably p, go to the left with probably minus p, right? And you want to look for f0n. Oh, sorry, fin, right? Probably if you ever go to n from I. Right. So let's say this, right? Why do you even care about a problem like the Gambler's Ruin? I guess besides the fact that it's famous, right? It's well known. You should have heard about it in many circles. The first thing, right, is that it is connected to, right, this topic of calculating the transition probability, right? The eventual, right? Eventual transition probability to go from I to N, right? So it's like F sub I, but now it's F sub I N, right? The probability of ever going to N starting from I, right? So that topic we'll explore deeply in the lecture after the next. But here's another, let's say, more mundane, practical question, right? And we can tell a story here, right? Just to kind of motivate. Let's say that, right? You have, let's say, a fancy restaurant, right? Or, Michelin rated, or, a concert you want to go to, right? That costs $100. Right now, right? Let's say in your pocket, you only have $50, right? And let's say that, right? You need to make up, right? Then the $50 difference somehow, right? And let's say that, you heard some, let's say, rumors, right? That there's like a illegal gambling joint, right? Operated by a certain Rutgers math professor. Okay. You can make bets, right? Now, the bet is very simple, right? You flip a coin, right? You win the amount you bet, right? If not, you lose the amount you bet. But notice, right? You have a flexibility here. You can either go all in and bet $50 at a time, or you can just break it down to small games, maybe $1 at a time. Question: do the two strategy are the two strategies equivalent, or is one strategy better than the other? Just get the pain over with, right? Either go big or go home, or let's enjoy it while it lasts. What do you think? Does it matter?
Does it depend on P?
Excellent answer. The answer is, of course, right? I mean, here, the rational answer depends on which strategy gives you a higher probability, right, of getting there, meaning the FIN here, right? Whichever gives you a higher probability, you should go with that, right? Let's say that you have all the time in the world, right, to do this. So time is not a factor. But, right, even then, right, the answer would depend on P, right? Whether the game is in your favor or not in your favor, right? And I think, right, already intuitively, you could see, right, that if the game is in your favor, what do you think? Meaning if P is bigger than 1/2, then should you go all in, or should you do it slow?
Like
What do you
small
think?
bets are better if P is greater than 1/2?
Intuitively, right, if P is bigger than 1/2, seems like the small bet is better. But notice, right, you still, right, from a mathematical point of view, have to establish why, right? Clearly, of course, if you do one single bet, then the probability, right, is 1/2, right? Sorry, it's P, right? But small bet, is it bigger than that, right? And then even more minutely, how much bigger? Because, for example, right, let's say you have all the time in the world, right? But let's say that, right, to push this example a bit further, right? If you bet one game at a time, or, right, you don't have to. Maybe you can do 2 at a time, correct? or 10 at a time, right? I mean, small bet doesn't have to be. Each of these clearly have a different grades, right? I mean, different probability. And you might want to choose a strategy that fits, right, your probability and your risk preference and your time, right? I mean, clearly, probably breaking down to, right, $1 at a time or even less will make you probably higher, but you don't have the time, right, to play 50 games. And maybe the chance, right, improvement is not that much, right, to worth your trouble. Does it make sense? So all of this, right, hopefully convince you on why, let's say, this calculation is meaningful in some way, right? Okay. So that's the point, at least, right? So the answer is right here, right? So it gives you the answer, and it'll show, right, exactly how the answer depends on P. All right, and we're just gonna derive the answers here after this. Any question about this? All right, so how do we derive the answer? We derive the answer by surprise, surprise, right? First step analysis. And so, right, the notation here is PI, and it's unfortunate, but you can also look at a small piece of I, right? This is just a notation. It really, right, should be looked at as FIN, the probability of going from, right, getting absorbed to N by I, from I, okay? And the first step analysis says, well, go to the right and go to the left, right, accordingly. Notice, right, problem like this has a boundary condition. For I equal to 0 and I equals to N, right? What are they? For example, right, what's P sub 0 and what's P sub N? P sub 0 is 0, right? Because if you go broke, you cannot bet again. You can never go to N. And P sub N is 1, right? You're already there. Is that okay? And, right, so ultimately what happens is you have a system of, right, this is so-called difference equations to solve, right? The first step analysis, right, notice usually doesn't hand you the answer onto your lap. It'll give you a bunch of equations to solve. And it's the solving of those equations are the painful aspect, or the research aspect, if you will, right? I mean, I'm not saying any kind of research, but let's say some research problem would focus on what's a good way to solve, let's say, a system equation arising from a problem, right? So, but here, lucky for us, right? The structure actually is very nice in the sense that this is a telescoping sum, and this is a power series. This is a geometric series. Okay. So couple, right, with the boundary condition, you can solve for all of these accordingly. So that's it.
Could you go? Sorry, could you go
Yeah,
back
go
up
ahead.
one slide?
Sure.
Thank you.
Yep.
Thank you.
Mm-hmm. Right. And so that's it, right? So again, right, I mean, the answers here are, let's say, not fundamental to us in the understanding of Markov chain overall, right? The problem, okay, is fundamental to us in the sense that it shows us a way to calculate the probability of eventually going to a recurring state, right? And it's recurrent from a transient state. That's going to be a recurring problem we'll be looking at later on, okay? And if you're into like gaming, right, and betting and strategy, that kind of thing, then this problem showcase the difference in strategies to achieve the same goal. And it's a very real kind of approach, right? Research problem. Again, I don't want to throw the word research in. It's like, hey, there's a research there, what kind of thing. But meaning like for a specific game, right? There's not just one single way to approach the goal. Even like breaking down, right? The path into small steps like this could affect, right? The winning probability, things like that. So this can also be viewed from that point of view, right? The actual answer, okay, fine. I mean, right, there's also the technical aspect of it that's worth studying, which is the first step analysis and the system of difference equations that arise from it. And trust me, right, there is course, right, in discrete math that teach you how to solve difference equation in general. As far as I know, they're not fun to solve. I mean, they're okay to solve, but here the structure is very, very nice, which gives rise to a nice solution, right? If you want to call this nice, but trust me, right, is as nice as it can get. The actual answer, okay, right, who cares? I mean, you can look it up, but the meaning and the structure of the problem is what you should kind of carry with you. All right, we're good? Any question? All right, if not, then let's continue on Wednesday, okay? Remember, there's a midterm on Friday, right? Midterm 2, and the structure will be the same, right, as midterm 1, okay?
Thank you.
Sure.
Thank you, Professor.
Yeah.
Thank you, Professor.
Yeah, thank you.
Hi, Professor Pham.
Yeah.
Could you possibly open your email right now and read my most recent email to you? Wait, if anyone else has any questions, please ask. This is like a personal question.
Hold on, let me just stop share, maybe. Stop recording.